So in this video we're going to look at Cauchy sequences of real numbers. So we'll begin with the definition of a Cauchy sequence. So the whole idea here is that when Cauchy came up with this idea of a Cauchy sequence, he was thinking about how can we test for whether a sequence is going to converge or not. That's the whole thing that we're aiming for. We are trying to work out tricks to prove that sequences are going to converge to a limit. And Cauchy came up with this property, the Cauchy property, the property that defines Cauchy sequences, thinking that if sequences obey this property, they're probably going to converge. Now, it turns out to be extremely interesting. In the rational numbers, you can define the concept of a Cauchy sequence, and in the rational numbers, it's not going to be true necessarily that all Cauchy sequences converge. Whereas in the real numbers, where we have the completeness axiom, the least upper bound axiom, that actually ends up meaning that all Cauchy sequences are going to be convergent. So we'll discuss that more later on in the video. So let's begin with the definition then. So we're going to have some sequence then, so A1, A2, A3, etc. And for this sequence to be Cauchy, this is the rule that it has to obey. It has to be the case that for all epsilon greater than 0, so at the moment this looks very similar to the definition for it to be convergent to a limit L, but it's going to be different to that. So for all epsilon greater than 0, there must exist a big N is an element of the natural numbers, so a big nth term, such that for all terms beyond it, and this time we're going to need two terms beyond it, so for all little n1 and little n2, which are both greater than or equal to n, the distance between the terms, and I'm just about to write something wrong there, I was about to write x, but we're calling the terms of our sequence a's, so a n1 subtract a n2, modulus of that difference between them is going to be less than epsilon. So what does this mean? This means that the terms of the sequence are going to get and stay indefinitely close to one another. So for it to be convergent to a limit, let's say L, we know that the terms of the sequence have to get and stay indefinitely close to that limit L. So given any epsilon interval around L, you have to be able to find a term in the sequence such that that term and all terms beyond it are inside that epsilon interval. That's not what we're saying here. Instead, we're saying that no matter how close you want to be, given any epsilon, I can find a point in this sequence. So I'm just going to rub a little bit of this out. So let's rub this out so that we can write some stuff there. So I have to find an A big N such that if you take any two terms that are beyond that big AN, so in that tail end of the sequence, so we have here AN1 and AN2. N2 isn't necessarily bigger than N1, it could be the other way around, but without loss of generality we can put them like this in the picture. So if you take any 2 points in this tail end of the sequence and look at how far away they are from one another, it's going to be less than epsilon, and you have to be able to find such a big N for whatever epsilon. So this is effectively saying that the terms of the sequence are going to get indefinitely close to one another and stay indefinitely close to one another, because it's not just that there are terms which get indefinitely close to one another, it's that there's a point where for all the terms after that they are in that close to one another. So they get to and stay indefinitely close to one another. So let's just explore a little bit more the intuition behind why Cauchy thought that that would be an interesting property. So if we have the real line again here, and let's put in blue the terms of our sequence, so imagine 1 is there, 1 is there, 1 is there, like so, and it might be dotting around, so it might be jumping over the place. But if it's going to be Cauchy, then the terms of the sequence are eventually going to need to get and stay indefinitely close to one another. So tiny this epsilon could get. So at some point these terms are going to have to accumulate up somewhere was the idea, because otherwise how can they possibly get indefinitely close to one another? If they're still jumping around all over the place in the real line, then they can't be getting indefinitely close to one another. So the idea was, if we restrict the behavior to this, to say that they have to be getting indefinitely close to one another, that must surely mean that they end up accumulating towards some sort of point, and therefore there must be a limit. That was the idea. And as we'll see, this is absolutely bang on in the real numbers. Cauchy sequences are all convergent in the real numbers, but that's not true in a structure like the rationals, where there are wholes, for instance the square root of 2, because actually, as I'll show you later on, we can create a Cauchy sequence that is going to converge down to the square root of 2, where all the terms of that sequence are actually going to be rational numbers. So it's going to be a sequence within the rational numbers, and it's still going to obey the Cauchy criterion in the rational numbers, but the limit that it's converging to, the point that it's actually getting closer and closer to, isn't actually in the rationals. So it's actually converging to something that doesn't exist there, a whole. So it's not convergent. It doesn't have a limit in the rational numbers. So in the rational numbers where there are wholes, Cauchy sequences aren't all going to be convergent, but in the real numbers where everything's complete and there are no wholes, it will turn out that all Cauchy sequences are convergent. Before we go on to that, however, let's first discuss something simpler, and that is the fact that if a sequence is convergent, it is Cauchy. So if we have a convergent sequence, it's going to imply that it's also Cauchy, and this is going to hold true in the real numbers, and it's also going to hold true in the rational numbers, which is, after all, just a subset of the real numbers. And then we'll do the more difficult backwards arrow, that if it's Cauchy, it's going to be convergent, and that's only going to hold true in the real numbers. So let's go forward firstly. So let's take some sequence A then, and let's say now that it has some limit. So we'll call that limit A. And we want to prove that this sequence is going to also be Cauchy. So to do this then, we need to show that for a general epsilon, you can find a big N such that this is going to hold true. So let's begin then by saying take a general epsilon, so let epsilon be greater than 0, and we now need to find this big N. So how are we going to do this? Well, we know that the sequence converges to a limit A. So here's the brilliant idea. Consider an interval around A of radius epsilon over 2. So this upper end is A plus epsilon over 2, and this lower bound is A minus epsilon over 2. Now, because this sequence converges, there must exist a big N such that for that big nth term and all the terms beyond it, they are inside this epsilon over 2 interval. Now, I claim that you can use that same big N that you got from here as your big N for the Cauchy criterion that I need to find here. And this is the reason, and that's the reason I've chosen epsilon over 2 here. Because we can now apply the triangle inequality. So we know that all terms from, if we take two terms of the sequence that are beyond big N, so let's take n1 and n2 greater than or equal to big N, so let n1 and n2 be greater than or equal to big N. They're going to be inside that interval is what we now know, an1, an2, because that's how we found big N. It was the term for which all the terms beyond it are inside that interval, that epsilon over 2 interval. So what is the maximum distance they can be apart from one another? Well, it's the distance from 1 to epsilon plus the distance from epsilon to the other by the triangle inequality. So if we then consider mod of an1 minus an2, we can rewrite this as an1 minus a plus a minus an2. That's just subtracting off a and adding a. And then we can apply the triangle inequality where this is one thing and this is the other thing. So remember, the triangle inequality says that the absolute value of x plus y is less than or equal to x, mod of x plus mod of y. That's the triangle inequality in the real numbers. It's not got much to do with triangles. It's called the triangle inequality because in higher dimensions, such as 2-dimensional and 3-dimensional real vector spaces, then it relates to the sides of a triangle. But we're using it here in the real line, and it does hold true. I've got a video where we prove this in the playlist on real analysis. So we're going to apply it here using this as x and this as y to say that this thing and therefore this thing is less than or equal to mod an1 minus a plus mod a minus an2. And of course both of those things in turn are less than epsilon over 2, so we know an1 minus a is less than epsilon over 2 and an2 minus a is less than epsilon over 2. So you can combine those two inequalities. Officially the way you'd do this is you'd imagine adding this onto both sides of this inequality. You'd then have this thing here is less than epsilon over 2 plus this, and then you just add epsilon over 2 onto both sides of this to get this thing plus epsilon over 2 is less than epsilon over 2 plus epsilon over 2, which is epsilon over all, and then you'd have this thing is less than epsilon by transitivity. So we can say that that is less than epsilon. And then finally, by transitivity, because this is less than or equal to this thing, which is less than epsilon, we know that this is less than epsilon. So what we've shown is that if we find this big N, where all the terms beyond it are inside this epsilon over 2 radius interval around A, then if we take any two terms beyond that big N and look at how far apart they are, then the maximum distance they can be apart is the length of this one to the limit A and the length of the limit A to the other one. And that's going to be the maximum. And that would actually be the answer if they were on either side of the limit, as this picture shows. Of course, if they're on the same side of the limit, so if you had the 2 points in blue here instead, then the difference between them is actually going to be much less than this thing, because it's going to be that little length there, whereas the length that you're actually taking is the length of this one to the limit, that length, and then the length of the other one to the limit, and adding them together. So that's why this inequality holds true in the real line. That's the visual interpretation of what this means, the triangle inequality. And it's kind of like the sides of a triangle, but squashed into one dimension. So overall then, we have shown that any two terms beyond that big N are going to be a distance apart less than epsilon if they're both inside that epsilon over 2 radius interval around A. And therefore we can use that big N as our big N up here in the Cauchy criterion. So we took a general epsilon, we have found a big N such that this is true, therefore we can do it for any epsilon greater than 0, and therefore this does hold true. So any sequence that converges is indeed Cauchy. Now that's useful in its own right, because it means that if you can show that a sequence isn't Cauchy, then you know immediately that that sequence can't possibly be convergent, and in some situations it's actually easier to show that it's not Cauchy than it is to directly show that it's not convergent. So it's a trick that you can use to prove non-convergence of a sequence by showing that it's not Cauchy. What we're now going to move on to then is this reverse question of showing that if it is Cauchy, it's then also true that it's convergent, which is something that's going to be true in the real line. So to do this, we are going to use a theorem from real analysis that I'm going to state here, but we're not going to prove it. If you want to see the proof of it, I do have a video on this theorem in the playlist on real analysis, and in that video we do prove it. So it's called the Bolzano-Weierstrass theorem, and the video is also just called the Bolzano-Weierstrass theorem. So here we're just going to state it. So it says that if you have a sequence an, and by the way, this theorem is true. It's about sequences, and it's true in the real line. It's not true in the rational numbers, and that's the reason that this proof that we're about to do, that Cauchy sequences are convergent, only works in the real numbers and doesn't work in the rational numbers, because the theorem which we're going to use, the whole basis for the proof, only applies to the reals and not the rationals. So this is going to be a sequence in the real line. So an is our sequence, and the second crucial criterion is that it must be bounded. So that means that there is some number that is bigger than all the terms, and there is some number that is smaller than all the terms. So we have some u which is greater than or equal to all the terms of the sequence. So for all n is an element of the natural numbers, and because we're not including the 0th term, we'll take away 0. and there is some L that is less than or equal to all the terms of the sequence. So on a picture, here's the real line, here is L, here is U, and this simply means that all the terms of that sequence AN are going to be inside this closed interval from L to U. So an example of a sequence that is not bounded would be the sequence AN is equal to N, so the sequence 1, 2, 3, 4, 5, 6, 7, 8, etc. Obviously that goes off and off and off, and there is no real number that's bigger than all the natural numbers, so that sequence quite clearly is not bounded above. It's beautifully bounded below. -1 is an example of a lower bound for that sequence, but it's not bounded above. So it needs to be bounded on both sides for this theorem to apply. So the theorem says then that if you have a bounded sequence within the real line, then that sequence might not necessarily be convergent. However, what will be true is that there is a subsequence that is convergent. So I'm going to say that again. Any bounded sequence in the real line will have a convergent subsequence. That is what the Bolzano-Weierstrass theorem says. So let me just give you a beautiful example of this. Take this sequence 1, 0, 1, 0, 1, 0, etc. We just alternate between 1 and 0 over and over again. So on a picture, here is 0, here is 1, and it flits between the two. Now that has no limit because there is no point where the terms get to and stay indefinitely close to. Because if you try and make it 0, then you can't find a term in that sequence where all the points are indefinitely close to 0. So for instance, if I took the epsilon equal to a half, I cannot find you a big N such that all the terms of the sequence beyond that big N are inside here, because if N is inside there, it will be 0, and if then N plus 1 will be back to 1 again. So there's no big N where all of the terms after it are going to be inside that half interval. So it's not true that it converges to 0, and the same argument holds for 1. However, it is a bounded sequence. Quite clearly it's bounded above by, let's say, 2, bounded below by -1. So we should be able to apply the Bolzano-Weierstrass theorem, which says that there must exist a convergent subsequence, and clearly in this case there are loads of convergent subsequences. In particular, there are 2 limits that convergent subsequences can converge to. So we could take the sequence that is just 1, 1, 1, 1, so we get rid of all the even terms and just keep the odd terms. That's a subsequence, and that clearly has the limit 1. Alternatively, we could take the subsequence where we take all the even terms, so we just get 0, 0, 0, etc. And that clearly is a convergent subsequence as well, converging to 0. So there are those 2 separate limits that subsequences can converge to. Another example of a subsequence would be 1, 0, 1, 0, and then after that I'm just going to take the terms that are 1, so only the odd terms after that. So yes, okay, it's looking a bit odd up here in the finite first 4 terms, but then the tail end is just 1, 1, 1, 1, 1, 1, 1, and therefore this is going to be a convergent subsequence converging to 1. So there's not just 2 subsequences of this, there's actually an infinite number of subsequences that are going to converge. There's just only 2 limits that a subsequence, if it is convergent, can converge to. Now that's a fairly trivial example just to give you some intuition. However, what this theorem is saying is actually much deeper than that example, because we could have sequences that are far less obviously patterned than this one, that are bounded. So let's go back to this picture here. So all the terms of the sequence are now going to be in this closed interval from L to U. And what this theorem is saying actually is that they can't not accumulate somewhere. So if you imagine them in here, because there's an infinite number of them, you can imagine trying to keep them apart from one another so that they're not accumulating up to some point that could then be a limit of a subsequence. And what this theorem is saying is that that's not possible. Somewhere, if they're in this bounded interval, the infinite number of points are going to have to accumulate up somewhere. So there has to be some point where they are accumulating up at. And it might be the case that, the sequence is then dotting around away from that point of accumulation. So overall it doesn't converge. Like, for example, this example where it continues to dot between 0 and 1, 0 and 1. So it's accumulating at 1 and it's accumulating at 0. So you've got an infinite number of points that are converging, if you like, to 0. They are all obviously equal to 0, so they're not just converging to it, they are actually it. But you've got an infinite number of points or terms at these 2 points. So they are points where the sequence is accumulating. So it can be dotting between the different accumulation points, or so that overall it isn't a convergent sequence, but there has to be somewhere where they are accumulating. So if the sequence is convergent, it will be the case that there's only one point where they're accumulating up at. Whereas if the sequence is non-convergent, it'll be the case that there are multiple accumulation points, or at the very least 2, so that the reason it's not convergent is that it's dotting between the 2 accumulation points, like in this example. And what this theorem then is saying is that we can take a subsequence so that we're just taking terms into our subsequence that are the ones that are accumulating up at one of these points, and omit all the ones that are jumping back towards a different, or potentially multiple different accumulation points. So we can omit all of them, and therefore we'll get a sequence that just accumulates up to one point and therefore is convergent. So that's what the Bolzano-Weierstrass theorem is really capturing, the fact that if you have a bounded sequence in the real line, because it's an infinite number of terms, they have to be accumulating up somewhere, and if it's non-convergent in the real line, the only reason that that can be happening, because there are no holes in the real line, is because there are multiple different accumulation points. In the rational numbers, it doesn't hold true because the terms might be accumulating up to just one point, but that point that they're accumulating up to is a hole in the rational numbers, such as the square root of 2. So it's only the case that this theorem holds true in the reals, because in the reals there are no holes. So the reason that it's not convergent is that it's got multiple accumulation points, and therefore you can get rid of that problem by just taking a subsequence and omitting all the points that are flitting back towards different accumulation points and just keep the ones that are accumulating to 1. So the way we're going to proceed next is to show that all Cauchy sequences are bounded, and therefore we can apply the Bolzano-Weierstrass theorem and say that a Cauchy sequence is going to therefore have a convergent subsequence. And we'll then show that if it has a convergent subsequence, and it's also true that it's Cauchy, meaning that the terms of the sequence get to and stay indefinitely close to one another, then the entire sequence must converge to the same limit as that convergent subsequence, and therefore the Cauchy sequence is convergent. So let's begin by showing then that a Cauchy sequence is bounded. So this follows from the fact that it has the Cauchy property, so we can just use epsilon equal to 1. So if I go back up here where the Cauchy property is actually stated, we can just take an epsilon equal to 1, let's say, and we can then find a big N such that beyond that, if you look at the distance between any 2 terms, it's going to be less than 1. So if we then consider where that term a big N is, and we consider the epsilon interval around it, so this is a big N plus 1, remember my epsilon was 1, and this is a big N minus 1, then all the terms beyond that, so if I make little n1 equal to big N, and then I just make little n2, then some other random term, they must all be inside this size 1 interval around an, because if I let little n1 be n, then I let this be any of the other terms, they must then be a distance less than 1 apart from one another. So actually I can say that for all the little n's greater than or equal to big N, they're going to be inside this interval. So here is a general one there. So little an is an element of this interval around a big N. Let me just move the board. Good. So then all of those terms beyond big N are going to be bounded above by an plus 1 and bounded below by an minus 1. So now all we have to consider is all the terms prior to big N term. but there are only finitely many of those, so they might be outside of this size 1 interval. They might be dotted around, so these in blue are representing them. So they might be dotted around out here. However, there's a finite number of them, so you just need to go through all of them, and you will then be able to find, the maximum one and the smallest one, because it's a finite set of them, and then you just need to overall combine that information with the information here about the bounds for this infinite tail of the sequence, and overall you can then construct some number that is bigger than all of the infinite number inside here, and then the finite number that go before it, and some number that's below all of them down here. So that's the proof then that any Cauchy sequence is going to be a bounded sequence. So now what we can do is apply the Bolzano-Weierstrass theorem to say that it must then have a convergent subsequence. So we'll call our convergent subsequence, I don't want it in blue, we'll call our convergent subsequence A sub n sub I, and we'll say that this converges to a limit L. And what we now want to do is prove that the entire sequence must converge to that limit L. So we want to prove that an converges to the limit L. Now, the intuition behind why this is going to work is here we have our limit of the subsequence L, and let's draw in blue. Here are the terms of the subsequence getting closer and closer and closer and closer, indefinitely close, and staying indefinitely close to that limit L. But we also know that the overall sequence is Cauchy, and therefore that the terms of the sequence are getting and staying indefinitely close to each other. So the other terms of the sequence that aren't in the subsequence, which I'm going to paint on in red, they can appear here, and I'm not sure how well they're going to show up, but they have to get indefinitely close to those other terms of the sequence, and those other terms of the sequence are included, some of them, in that subsequence. So there's an infinite number of them in this subsequence. Any tail end of this sequence has a whole bunch of them in the subsequence. So they also have to be getting indefinitely close to this subsequence as that subsequence gets indefinitely close to the limit L. So overall, they're also going to follow the subsequence in to that limit L. That's the intuition here. So to prove this then, what we need to show is for all epsilon, so we'll let epsilon be greater than 0, we need to show that there exists a big N such that for that big N and all terms after it, all of the terms of the sequence are going to be inside this epsilon interval around L. So the way we're going to find that big N is we're going to apply the epsilon definition of the convergence of the subsequence for epsilon over 2. So here is an epsilon over 2 radius interval around L. So because the subsequence converges, there must exist a term in that subsequence. So there must exist what we'll call the big I, is an element of the natural numbers, such that for all little I is greater than or equal to big I, the distance between a, n, I and that limit a is less than epsilon over 2. So from, if we put this on the picture, let's say this point here is a, n, sub I, so some term in the subsequence, it's inside that epsilon over 2 interval, and all of the terms in the subsequence after it are also inside that epsilon over 2 interval. Now we're going to apply the Cauchy property, which we know holds true for our whole sequence A. So we'll use epsilon over 2 again. So the fact that it's Cauchy tells us that there must exist some, what we'll call big M1, which is a term in the sequence, such that for all little m1 and little m2 beyond big M1, the terms of the sequence are less than epsilon over 2 apart from one another. So if you look at how far apart the terms of the sequence are, it's going to be less than epsilon over 2. And this is the genius idea. Because you know all the terms of the subsequence are inside this epsilon over 2 interval, and you know that the maximum distance terms can be apart is going to be less than epsilon over 2 once we're past m1, if we just make sure that we're past both of these, then both of them are going to apply, and then we can use the triangle inequality to say that the maximum distance that any point, therefore, in the overall sequence can be from the limit L is going to be less than epsilon, because it's going to be less than epsilon over 2 to the nearest, or to a point in the subsequence, and then from a point in the subsequence to another point in the sequence, it's going to be less than epsilon over 2 as well. So that's the basic idea. So to draw a picture to illustrate this better, let's firstly draw out our subsequence here. So we have an1, an2, and then we've got further down the line this ani, and we're saying beyond that all the terms are inside that epsilon over 2 interval. And then, making some more space here, we've got the larger sequence, a1, a2, etc. And then we've got this point a sub m1, where beyond that the distance that the terms are apart from one another is less than epsilon over 2. And what we've now got to remember is that this is a subsequence of this, so this is part of this sequence. All of these terms that are in this subsequence appear here somewhere as well. So this term here, this an sub big I, it might be downstream of this one. It might be bigger than this one, or it might be lower than this one. And we're going to treat those two cases separately. So we'll start off with the case that an sub I is downstream of an1. But before we just do that, I'd just like to correct something that's written over here. So I have written in here little a to mean the limit, or the proposed limit of our sequence, the known limit of the subsequence. However, up here we've been denoting that L, here we've denoted that L, in the picture we've denoted it L, so I shouldn't have just suddenly moved to calling it A here. I apologise for that if that's confused anyone, so that should be L. I hope all of you realise that whilst you're watching. So let's go back to where we were then. So we're now assuming that an sub I is downstream in the overall sequence of an1. That is to say that n sub big I is greater than or equal to big M1. And now my claim is that I can use big M1 as our big N to prove that the overall sequence converges, or to show that I can find a big N such that for that term and all terms onwards, they are inside this epsilon interval around L. So my claim is that if I set big N equal to big M1, that for all little n greater than or equal to big N, it's going to be the case that mod an minus the limit L, called the correct thing this time, is going to be less than epsilon. So why is it that I can know that? So let's do this. Let's take some n then that's greater than or equal to big N, and that is of course equal to n1. So it's some term in the sequence that's downstream of here, and I want to see why this is going to be true. Well, I can now use the triangle inequality. I can write this as an minus, and then the thing that I'm going to add in here, or subtract and then add back on, is going to be my famous term an sub I, which is somewhere, we're saying, down here, like so. So I'm going to subtract that off, I'm going to add it back on again, and then we'll have our minus L there. So nothing dodgy's happened there. What I can now say is that this thing, by the triangle inequality, is less than or equal to an minus ani plus ani minus L. And now what do I know? So by the fact that ni was chosen because it was the term that was going to be inside the epsilon over 2 interval, and all terms after it were going to be inside that epsilon over 2 interval. So by this here, I can say that this thing is less than epsilon over 2, so I'll just write that over here. So an sub I minus L is going to be less than epsilon over 2. And then by the Cauchy property, I've got here two terms, an and ani. Both of them are now beyond this m1, and therefore the difference between them is going to be less than epsilon over 2. So putting those two inequalities together, I can then say that these two things added together is going to be less than epsilon. So this is less than epsilon. And then by transitivity, this initial thing is less than or equal to this, which is less than epsilon. So this is therefore going to be less than epsilon as desired. On the picture, what we've done is here is ANI, and we've said because ANI is in this tail end of the sequence, for which if you take any two terms in this tail end that's beyond this N1, the distance between them is less than epsilon over 2. I've said what we can now do is imagine, I could try and draw it on this picture, but it's going to get incredibly crowded. Imagine putting an epsilon over 2 size interval around an sub I, and I think, in fact, I will try and draw it. I'll draw it in a different colour. We'll go green. So here is kind of that epsilon over 2 size interval around an sub I. And now, because it's in the tail end of this Cauchy sequence, we know that all the terms in this tail end must be inside that interval, and that epsilon over 2 interval is then going to lie inside the overall epsilon interval, because that's the reason I used epsilon over 2 for both the convergence of the subsequence and the Cauchy criterion, so that overall, when we have both of these intervals on top of one another, it's overall going to lie inside that larger epsilon interval. Now for the second case then, so let's say now that this isn't downstream of this, so it's actually upstream of it, so Ni is now going to be less than M1. Now that's a problem. It means we can't use ANI in the way we did here, because if we do use it like this sort of magic trick here, apply the triangle inequality, this thing's still going to be fine. We're still going to know this is less than epsilon over 2. It's this that we've got a problem with. We're not going to be able to conclude that the distance between any term a little n and a ni is less than epsilon over 2, because this term was upstream of that tail end for which the Cauchy criterion applies at epsilon over 2. So what instead we need to do is we need to go on in our subsequence, and we need to continue on until we get to a term that's actually inside this tail end of the sequence. And such a term will exist because obviously this goes on forever and there's only a finite number of terms ahead of this tail end. So at some point you must get to a term in the subsequence that is actually inside this tail end. So we'll call that term an sub I, and we'll call that I bar. And then all we're going to do is substitute in here, instead of using ANI, we'll use ANI bar. So here's ANI bar inside that tail end. We'll just substitute this in instead, and the exact same magic trick is going to occur, that if you want to know how far AN is from the limit, it's going to be less than or equal to how far AN is from ANI bar plus how far ANI bar is from L. Now, how far is ANI bar from L? Well, it's also going to be less than or equal to epsilon over 2 because it's further along in this subsequence than ANI, and by the definition of convergence, this was the term for which it and all the terms after it are inside that epsilon over 2 interval around L. So we can add a bar there, and that's still going to hold true. And then this inequality is also going to hold true because it's now downstream of AN1, and then the Cauchy criterion applies that if you compare any term that's downstream of this and to this one and look at how far apart they are, it's going to be less than epsilon over 2. So overall, what I've done is I've taken a general epsilon and I've shown I can find you a big N such that that term of the sequence and all terms beyond it are going to be inside that epsilon interval, and that means that I've proven that the overall sequence converges to the limit L. And hence we have shown that if you have a Cauchy sequence in the real line, it's going to be bounded by the Bolzano-Weierstrass theorem. It's going to have a convergent subsequence, and having that convergent subsequence plus the Cauchy criterion means that overall the sequence is convergent. So overall, all Cauchy sequences in the real line will converge. Next, what I'd like to do is just demonstrate by means of a counterexample how that is not true in the rational numbers. So I just want to show you an example of a sequence that is going to be Cauchy inside the rational numbers, but is not going to converge to any limit inside the rational numbers. So we're now stepping out of the reals into the rationals. So this line is now representing the rationals. We're going to have 0 here, we're going to have 1 here, we're going to have 2 here. And the way we're going to do this is we're going to build a Cauchy sequence of rational numbers which is going to converge down to the square root of 2 in the real numbers, but of course the square root of 2 isn't in the rationals, so it's actually converging to a whole in the rational numbers. And that's the reason that Cauchy sequences fail to converge in the rational numbers, because they can, or fail in general to converge in the rational numbers. Of course, all convergent sequences are Cauchy, so any convergent sequence you have in the rationals will be a Cauchy sequence, but there are also examples of Cauchy sequences in the rationals that aren't convergent, and the reason is that they're converging down to some sort of whole inside the rationals. So it's going to converge then to the square root of 2, which, if we are cheeky for a moment and include it, it's roughly around there. So how are we going to build this? So we're going to start off with 1, 2, and we're going to gradually half the size of the interval. So the reason we've started with 1 and 2 is because we know that 1 squared is 1, and that is less than 2, and we know that 2 squared is equal to 4, and that is greater than 2. And from that we can conclude that 1 is less than this magic number that squares to 2, and that 2 is greater than this magic number that squares to 2. The reason for that is basic ordered field manipulation. If we know that x squared is greater than y squared, and both x and y are greater than 0, then a manipulation we can do is subtract y squared from both sides to get x squared minus y squared is greater than 0. We can then factorise this using the difference of 2 squareds into x minus y times x plus y is greater than 0. And now, because both x and y are greater than 0, we know that x plus y is greater than 0, so we have a multiplicative inverse for that. We can multiply through by its multiplicative inverse without changing the sign of the inequality, and then you get that x minus y is greater than 0, so x is greater than y. So if you are given that x squared is greater than y squared, and you are given that both x and y are positive, you can conclude from that that x is greater than y. So applying that here, we're going to have x initially, let's say, is this magic number that squares to 2. So x squared is going to be 2, and then y is going to be 1. So 1 squared is 1. So we've got that 2 is greater than 1, and we're using that to infer then that the square root of 2 is greater than 1. And then the opposite way round for 2. 2 is going to take the place of x, and y is now square root of 2 is taking the place of y. And then we've got 4 is greater than 2, and we're using that to infer that 2 is greater than the square root of 2. So that's basic ordered field manipulation there to justify the conclusion that I'm making, that if 1 squares to something that's less than 2, it is less than the square root of 2, and if 2 squares to something that's greater than 2, it is greater than the square root of 2. So back onto how we're going to construct our sequence. So we're going to bisect the interval. So the picture is very quickly going to become very crowded and not to scale. So that is not a perfect bisection of the interval, but it's the best I can do given the picture. So we're bisecting it, and that number there is now 1.5. And so we put 1.5 as our next number in the sequence. And then to find what the fourth term is going to be, we need to now adjust our interval, and we need to decide, is our next interval of size a half going to be the interval on the left, or is it going to be the interval on the right? And the way we do that is by looking at what 1.5 squared is equal to. So 1.5 squared is 2.25. That is greater than 2. So it now needs to replace the right-hand bound of the interval, not the left-hand bound, because we always want to keep the interval that contains the square root of 2. So if we were to keep this half, that would no longer contain the square root of 2, because both 1.5 and 2 squared is greater than 2. So we want to keep the left-hand interval. So we're going to go now to the left-hand interval. We're going to half it this time. So there's the half of that interval, and that will give us 1.25. That's going to be the next term in our sequence, and we will continue on in this fashion. So to get the fifth term, we'll then want to adjust our interval again, so we need to decide which of those two halves of this interval do we want, this half or this half. So again, we need to look at what 1.25 squared is equal to. There should be a squared there. So 1.25 can be written as 5 over 4. So that squared is going to be 25 over 16, and that is something that's less than 2, and therefore 1.25 is going to be less than the square root of 2. So we need to keep the interval from 1.25 to 1.5, which is now the interval that's going to contain the square root of 2. And then we continue on in this way. We'll bisect that interval. That term, that number, will be the next term in the sequence, and we'll decide which of the two halves of the interval we're going to keep. And we're always going to keep the side that still contains the square root of 2, and we're going to continue constructing a sequence like this. So this sequence is always going to be rationals because we're just halving intervals. We started with two rational numbers, and then we're going halfway in between each of the terms, and each time we go halfway we're going to get another rational. So all of these terms of this sequence are going to end up being rational numbers. So it's a rational sequence. It's going to be a Cauchy sequence. Hopefully that's obvious to you because of the fact that this interval is progressively getting smaller. It started off as 1. The interval is what, after all, the whole sequence is based around. The interval started off of length 1, then it goes to half, then it goes to quarter. It halves each time, so it's getting indefinitely smaller. And when you have your interval, you can find, so for any size interval, you can find a point in the sequence that relates to that interval, and then all the terms of the sequence beyond that are going to have to be inside that interval. So if you consider, for instance, the interval of size 1 over 2 to some power, so I'll just write some of this down. So we could consider 1 over 2 to some power n, where n is again a natural number, excluding, in fact actually we do want 0 because the initial one would be the interval of size 1. So all the intervals are going to be of this form or of this length, and you give me a natural number, so you give me 10 for instance. I can go along this sequence and I can find the terms which relate to that interval of size 1 over 2 to the power of 10. So the terms of the sequence are always relating to this, and then all the terms beyond that term will then have to be inside that interval because we're just getting smaller and smaller intervals. All the intervals are nested inside one another. So all the intervals onwards that the sequence is based on were inside previous ones. So because the intervals are getting indefinitely small, then the terms of the sequence must also be getting indefinitely close to one another. So that's why this sequence is going to be a Cauchy sequence within the rational numbers. Now, it's not going to be convergent because if we step back up into the real numbers for a moment, the value of what this is going to converge to is the square root of 2, the value that's inside all of the intervals. And the way to see that is quite simply, if you proposed that it converged to something else, well, it's a Cauchy sequence, so we know it has to converge now, as we've already demonstrated to some degree. If you believe in the Bolzano-Weierstrass theorem, we've demonstrated that it is going to converge. So I claim it can't converge to anything other than the square root of 2, because if you consider some number that isn't the square root of 2, there's going to be a distance in between x and the square root of 2. We'll call that L, and I can find you an interval. I can find you an n such that the size of this interval is smaller than that length between the square root of 2 and x. So at some point I'm going to be dealing with an interval of that size, that smaller size, that contains the square root of 2 but can't possibly contain x because its length is smaller than this length L between the square root of 2 and x. So that holds true for any x. Any x that isn't the square root of 2, I can find you an interval that is small enough that is going to at one point be crucial to my defining of this sequence, where only terms inside the interval, only numbers inside the interval are candidates for future terms in the sequence, and therefore all of those other terms of the sequence cannot possibly be going and converging to x. So hopefully that's convinced you that it will converge to the square root of 2 in the real numbers. Now step back out into the rational numbers and consider it can't converge to something separate in the rational numbers, because if it did, then that number is still in the real numbers, so it would have to converge to it also in the real numbers, and then it would contradict what we've just argued, that it can't converge to anything that isn't the square root of 2. But the square root of 2 isn't in the rational numbers, so overall this sequence of rational numbers that is Cauchy is not going to have a limit inside the rational numbers. So I'm going to end this video with a really beautiful analytic discussion. So this video is in both the calculus playlist and the real analysis playlist. If you've come here from the calculus playlist, now might be the point that you want to leave, because we're going to go very much so into the territory of analysis here. We're going to discuss the real numbers, and we're going to discuss how actually the least upper bound axiom, which back in one of the initial videos in the real analysis playlist on the real numbers, we saw was one of the defining axioms of the real numbers. We characterized the real numbers in that video on the real numbers, and we saw the axioms they obey, and the least upper bound axiom was the final one we discussed, the one that separates the real numbers from the rationals and takes you truly into the realm of analysis and out of algebra. And it is actually equivalent to this concept of all Cauchy sequences converging. And you could actually, in your characterization of the real numbers, scrap the least upper bound axiom and instead put in the axiom that all Cauchy sequences must converge, and that would give you the exact same structure. It's an exact same characterization of the real numbers. So the least upper bound axiom and the fact that all Cauchy sequences converge are actually characterizing this same incredible property of the real numbers that we call completeness. And that's the reason we also call the least upper bound axiom the completeness axiom, and the fact that all Cauchy sequences converge is also called the completeness property of the real numbers, Cauchy completeness, if you like. So this is what I want to discuss. I want to discuss that the least upper bound axiom, which I will abbreviate as LUB, is equivalent, logically equivalent to Cauchy completeness, that will just denote CC. So just to outline a little bit here, so if you will need to get the complete picture here, you will need to have seen the proof of the Bolzano-Weierstrass theorem, and as I say, I've got a video proving that in the playlist on real analysis. So the way it works is the least upper bound axiom being true. So we're going to look at the forward direction first, and then we're going to look at the backward direction. So the least upper bound axiom being true gives rise to the monotone convergence theorem, MCT. That is, that all monotonically increasing and monotonically decreasing sequences that are bounded above and below respectively converge. That comes directly from the least upper bound axiom. You prove it by saying that if we're talking about a monotonically increasing sequence, the terms of the sequence will have a supremum if they're bounded above. If we're talking about a monotonically decreasing sequence, the terms of the sequence will have an infimum if they're bounded below. So it comes directly from the least upper bound axiom. And then the monotone convergence theorem is crucial in the proof of the Bolzano-Weierstrass theorem, and as I say, we do that in a separate video in the playlist on real analysis. And then from the Bolzano-Weierstrass theorem in this video, we have seen how that leads to Cauchy completeness. So that's the way you go in one direction. So the least upper bound axiom implies that all Cauchy sequences converge. And now what I want to convince you is the other way round. So if we start off with the real numbers instead defined with this Cauchy completeness axiom that all Cauchy sequences must converge, then we can get to the least upper bound axiom. And indeed, they're both capturing this same property that we don't want there to be any holes inside them. The least upper bound axiom was one way of capturing that we didn't want any holes, by saying that any set must have a least upper bound. So it cannot be that the boundary of a set is a hole in your structure. So if we draw the real line here, remember the problem with the rationals was we could consider the set of all numbers in the rationals that square to less than 2. So we consider this set of all x such that x is an element of the rational numbers, and, as that symbol means, and x squared is less than 2. So that's, and we'll make that, so we'll put it on the third criterion, then we'll just take the positive ones. That just simplifies things. So we'll add another, and x is greater than 0. So that's going to be all of these rationals here. And the problem in the rationals is that there is no boundary here. There's no value that forms this like boundary between these numbers that square to less than 2 and these numbers that square to be greater than 2, it's the boundary is a hole in the rational numbers. So by insisting on the least upper bound axiom that there is a boundary for every set, it plugs in all of those holes in the rationals when you go up to the real numbers. And this Cauchy completeness idea, the fact that all Cauchy sequences converge, again, this is going to plug in all the holes, because all these examples of sets where their boundary is one of these holes in the rationals, you could construct a Cauchy sequence again in the rationals that is converging to that hole. So by insisting that all Cauchy sequences converge, it actually plugs in the gaps just as well as the least upper bound axiom. So they are equivalent characterizations of this gap-filling axiom of the real numbers. The completeness axiom is what we overall term this idea, or the completeness property. So completeness axiom. So what I now want to do is just actually show you this other way around arrow. So I want to show you this, that if we start from the fact that all Cauchy sequences converge, that we can derive that all sequences that all sets that are bounded above have a least upper bound. So let's imagine then that we're in the real line and we now don't have the least upper bound axiom. Instead we have Cauchy completeness, so we know all Cauchy sequences must converge. And what we want to do is take a set that is going to be bounded above and we want to derive that it's going to have a least upper bound. And the way we're going to do that is by constructing a Cauchy sequence that is going to converge to a value that is going to fulfill the properties of the least upper bound for this set, which is that it needs to be an upper bound and it needs to be the smallest one, i.e. if you take any other upper bound, that must be greater than or equal to it. There is no other upper bound that is lower than it. So on our picture then, let's call our set S. Of course, it's not equal to the empty set, and to be honest, we might as well assume that it's an infinite set, because if it's a finite set, then it will have a maximum value, and that maximum value will fulfill the properties of the least upper bound. So we can draw our set on here. So it might have some points like so, and they might sort of like get very close to one another. So we've got some set like this. And what we know is that it's bounded above, so it's got an upper bound. So u is greater than or equal to all little s, where little s is an element of big S. And I now want to construct a Cauchy sequence that is going to converge to something that's going to be the supremum of this set. And this is the way I'm going to do it. I am going to do it in a very similar way to what we did previously, where we constructed a sequence that converges to the square root of 2. I'm going to construct intervals that are always going to contain the supremum, and the way they're going to always maintain the supremum inside them is that one side of the interval is going to be an element that is not an upper bound, and one side is going to be something that is an upper bound, and therefore in between them must be the actual least upper bound. Now this will become clearer to you as I actually construct my sequence. So I know what I'm going to use as the first upper bound boundary for my interval. It's going to be this u that we're given. I need something for the other bound of my interval, something that's not an upper bound. How am I going to do that? Well, I'm going to go to my set. I'm going to take an element inside of it, which I can do. So let's say we pick this element here, which is x. And either x is an upper bound, not very likely for this picture, or it is not an upper bound. Now, if x was an upper bound, then we're done, because x is then going to be supremum of the set S. Because if your set contains an upper bound, then that element is instantly the supremum. Let me explain the reasoning for that. This picture is extremely misleading, because on the picture it's not an upper bound, because more generally it's not going to be an upper bound. But imagine it's here now, and it is the upper bound for the set. So because it's an upper bound, it would be greater than or equal to S, little s, for all little s is an element of capital S. And the reason it would be a least upper bound is if you went to anything that was smaller than it. So for all y that is less than x, y cannot possibly be an upper bound anymore because it's less than x, and x is inside the set, so it's one of the elements of the set itself. So y cannot be an upper bound because it's now smaller than one of the elements of S. And the definition of being an upper bound is that you are greater than or equal to every element of the set. So the moment you have an upper bound that is actually in the set itself, that thing is immediately the least upper bound because of this argument that nothing that is smaller than it can be an upper bound. So it must be the least one, because anything that's smaller than it would be smaller than it, and it's in the set, so it would contradict this thing being an upper bound. So if you take by chance a value in the set that is an upper bound, you're done. You've got a least upper bound. So we might as well assume that x is not an upper bound. And we're therefore going to use it as our first term in the sequence. And the second term is going to be our u. So the way I'm going to construct this sequence is actually in probably a better way than I constructed that one for the square root of 2. I'm going to put pairs. So I'm not just going to define each element in turn, I'm actually going to define the elements in pairs. So each of the two pairs is going to be the sides of the interval. So here's the first pair, x and u, making up our first interval here. Then what we're going to do is we're going to go halfway in between the two. So we'll bisect it, and we'll get x, what I'll call x1, let's say, here. This one can be x0. I know I usually don't like indexing things 0, but we'll do it for this one, so I'll call that x0. So we've now gone halfway in between them. We've got this value x1 that's bisected our interval up, and then we can ask, is x1 an upper bound or is it not an upper bound? So we need to compare it to all the elements of the set. If it's greater than or equal to every single one of them, then it's an upper bound and it's going to replace u. If it's not greater than or equal to every single one of them, then one of them is bigger than it. Now, in this picture, it looks as though it's perfectly the least upper bound, but more generally it might not be, and there might be some elements of the set above it. So it's going to be one of the two. It's either going to be an upper bound or it's going to not be an upper bound, and there'll be elements of the set that are greater than it. So you will then replace whichever one is necessary. Now, in this case, I'll go with what the picture has here. So we'll keep x0 as our lower limit, or a lower bound of our interval, and we'll replace u with x1 as the upper bound. And this is what I mean by I'm going to define the terms in pairs. So I'm not just going to define one at a time, I'm going to define two at a time. So this is my first interval, and then I'm making term 3 and term 4 the boundaries of my second interval, and then term 5 and term 6 are going to be the boundaries of my third interval. So I've decided that x1 was an upper bound. It's bigger than or equal to all the blues as it appears to be on this picture, and therefore we're going to keep it like so. And then what you'll do is you'll go halfway in between this second interval that you've got, which is x0 and x1, and you'll get an x2 here. And then again you ask, is this thing an upper bound or is it not an upper bound? So you compare it to all the elements of the set S and see, is it greater than or equal to them? On this picture it clearly is not an upper bound because there's all these ones that are strictly greater than it. So it then needs to replace the thing that's not an upper bound, which is the left boundary of the interval. So it's going to replace x0. So our next thing along is going to be x2, and then we're going to repeat x1 again. So that value of x1 is going to appear again in the sequence. This is what I mean by saying I'm doing it in a more elegant way to how I did it previously with the square root of 2. I could have done the exact same thing where I defined pairs of terms in the sequence as the boundaries of my successive intervals. I could have done it for the square root of 2, and it probably would have actually made it simpler to understand for you. But for this one, I'm going to most definitely do it. So, and then you continue on. You keep going. So now we've got our interval x2 to x1, and you bisect that again, so you get x3 here, and again you ask, is x3 an upper bound or is it not an upper bound? Clearly here it's not an upper bound, so it's going to replace the lower bound of my interval. So next along is going to be x3, and then x1 is going to be repeated there because it's still the upper bound for my interval. And you'll continue on in this way, and clearly the size of the interval is getting halving each time. So here's where the brilliance happens. So this sequence is going to be a Cauchy sequence, and the reason that you can see that is the size of the interval on which it's based is always halving. So if we call this pair of terms the first pair, the first interval, this pair of terms the second pair, the second interval, this pair of terms the third pair, the third interval, then we can talk about the nth pair or the nth interval. And what's going to be its size? Well, the size of the first one is u minus x0, this size here, which is some finite value. And then subsequent ones are going to be divided by 2, however many times it takes to get there. So for the second one, that's going to be just dividing by 2 once. For the third one, you're going to have to divide by 2 and then divide by 2 again. For the fourth one, you're going to have to divide by 2, divide by 2, and divide by 2 again. So clearly you're going to have to divide by 2 n minus 1 times. So if we're talking about the nth interval, its size is going to be this. Now the other key thing to note is that if you go along to the nth interval, the nth pair of terms in this sequence, all the other terms after it are all going to be inside that interval. So if we look at the first interval, x0 and u, all subsequent terms of the sequence are going to be inside of it because of the way we're defining these intervals to be nested inside one another. Then if you look at the second interval, that's x0 to x1, again, if you look at all the downstream terms of the sequence, the tail end of the sequence, they're all inside it, again, because of how we're always bisecting and then taking an interval inside. So everything downstream is always inside of the interval that we're looking at. And therefore, the maximum distance between any two terms from the nth pair onwards, so if we've got our, let's say, nth pair here, so there's some term, well, I'll just make them squiggles rather than having to give them names, so that we've got this pair here that defines this nth interval. If you look at all terms after it and then you compare how far apart are any two terms, so the Cauchy idea, then it's always going to be less than the distance between these two, i.e. the length of the interval, because all of these points are inside the interval, so the maximum distance they can be apart is the length of the interval. So just to illustrate that, if I have an interval here, let's say lower L1, L2, and you take any 2 points inside that interval, the distance between them is less than or equal to the distance between the upper bound and the lower bound of the interval. It's not possible to suddenly to take 2 things that are inside this interval and get an absolute value of the difference between them, a distance between them bigger than L2 minus L1. So the maximum size of the difference between any two of the terms in this tail end of the sequence is going to be this. And this gets indefinitely small. Therefore, you can say that the terms of the sequence are going to get to and remain, because the whole tail of the sequence is going to obey this, indefinitely close to one another. It's going to obey the Cauchy criterion. So my initial assumption was that all Cauchy sequences converge in the real line. So because this is a Cauchy sequence, it is going to converge. It is going to have a limit. So we'll call that limit L. And we'll draw another picture here. So here is L. And now what I want you to note is that any subsequence of this sequence that converges to L is also going to converge to L. That's a basic property of subsequences. So I can construct 2 subsequences in particular. I can construct the subsequence of all the left terms of the interval. So I can go to each pair of terms and I can just take these ones, the ones that are all not upper bounds. So I've got this sequence then, this subsequence of things that are not lower bounds that is converging to L. So I'm going to draw this here. So here they are, x0, x0, x2, and then we had x3, and it goes on. So they're all the lower bounds of the intervals that we've used to construct this initial sequence. So these are all not upper bounds, which means that there exists some element in the set that is greater than them for every single one of them. And then we can construct the subsequence of all the things that are on the right for each of the pairs. So all the things that were upper bounds, the upper bounds of the intervals, and the things that were upper bounds for the set. So we'll draw this down here. So we've now got this sequence U, x1, x1, x1. So just to put some colour on this, here are all these things. We're going to take these to form this subsequence, and this is now a subsequence of things that are all upper bounds for the set. So the way they're defined, the way the intervals are set up, this sequence of things that are all upper bounds is going to be a monotonically decreasing sequence coming down to our limit here, because if you remember the way we got these, you couldn't suddenly go up. You were always replacing it with something that was lower than it. So it would either stay the same because you're using it again in your next interval, or it would go down because it's been replaced by something that is the bisection of it with the other end of your interval, and that thing that's in the middle will always be lower than it, so it's only ever going to go down, so it's a monotonically decreasing sequence that's coming down to your limit L. Meanwhile, let's colour in the other side, so these terms in red, the lower bounds of the interval, the things that are all not upper bounds for our set, these things here, and they are a monotonically increasing sequence that is coming up to the limit L, like so. And again, that comes from the way that we've constructed them. They were the boundaries of these intervals, and each time you were bisecting your current interval, and you were either keeping your lower bound and replacing your upper bound, or you were actually replacing your lower bound with the bisection, which of course is something that's going to be greater than it. So it's only ever going to stay the same or go up, so it's going to be monotonically increasing. So on this picture it looks like this. Now, I claim from this that I can now conclude that this limit L must be the supremum of the set S. So how can I do that? So my claim is that L is going to be the supremum of the set S. So we have to show that L is going to satisfy the properties of being a supremum of the set S. So the two properties that it needs to satisfy is, one, it must be an upper bound, and two, it cannot have another upper bound that's lower than it that is still an upper bound. So it must be the least one, the smallest of the upper bounds. So firstly, let's show that it is going to be an upper bound. So we'll do this by proof by contradiction. Suppose it wasn't an upper bound for the set S. That would mean that there was some element of the set S that was strictly greater than it. So we'll put this on the picture here. So that would mean there was some x here that was strictly greater than it. Now, why is that a problem? Well, this picture makes it very obvious why that's a problem, because this sequence of green things is converging to the limit L. So it gets indefinitely close to there, which means it's going to get closer than that difference between L and X. So L and X have some finite value in between them. The terms of the green sequence are going to get closer to L than that distance. Otherwise, they wouldn't converge if they didn't ever get closer. But that's a contradiction, because all of these green things are supposed to be upper bounds. So hence, it's nonsense. You can't have an element X from the set S that is strictly greater than L, and therefore L is greater than or equal to all X or S for the set S. So we can conclude that, I'm going to change my colour pen again. We can conclude that L has to be greater than or equal to S for all S is an element of S. Otherwise you'd have that contradiction that I've just produced there. And now I'm going to show that it must be the least upper bound, and we're going to show that by using the red sequence here, again by contradiction. So if it's not the least upper bound, then there would exist another upper bound that is strictly lower than it. So we'll call that, what can we call that? Let's call it, oh, come on, this isn't that difficult. U, we'll call it for upper bound, not to be confused with the other U that we've got. That was big U, this is little u. So suppose little u exists that is an upper bound for our set in blue here, that is strictly less than L. Now that's a problem because of the red sequence here that again is converging to the limit L, is getting indefinitely close, and therefore will at some point get closer to L than this distance between U and L. But that's a problem because U is supposed to be an upper bound, so it's supposed to be greater than or equal to every element of the set S, whereas these things in red, these are things that are not upper bounds. So how can we suddenly have something that's not an upper bound being bigger than something that is an upper bound? That's nonsense. It would break transitivity. If this thing in red is bigger than U, it would also be an upper bound for all the elements of the set, but it's not an upper bound. That was how that sequence was constructed. And therefore that contradicts the being able to be this upper bound that is strictly less than L. Therefore we can say that L is the least upper bound. So for all u, which is u, an upper bound, I'll put in brackets here, upper bound for S, u must be greater than or equal to L. It can't be strictly less than, otherwise this contradiction would arise. And therefore we have proven that L is an upper bound and L is in fact the least upper bound, so we've proven that this set does indeed have a supremum. So overall, the deep analytical lesson that we have learnt here is that the least upper bound axiom does lead to the fact that all Cauchy sequences converge, i.e. Cauchy completeness, and equivalently, if you start with Cauchy completeness, it implies the least upper bound axiom, so they are equivalent to one another. And indeed, actually, there's this great big loop here, so all of these are actually equivalent to one another. However, usually when we talk about this, we favoritize the least upper bound axiom and the Cauchy completeness axiom. But if you don't want to favoritize one over the other, you can just refer to the completeness property of the real numbers, which captures what all of these capture, this idea that there cannot be any holes in the real numbers. So that's the completeness axiom, or the completeness properties of the real numbers. But we do usually, however, having said that, favoritize the least upper bound axiom or Cauchy completeness. So we either write one of the two in our characterization of the real numbers. And with that, we will end this video. Thank you for watching.